Hi everybody and welcome to AP Chem video. This is Mrs. Hanson. Today we are talking about the equilibrium expressions in K. Okay, so this is page 618 to 633 in your book. I definitely recommend that you read this, but let's start with K. So we're talking about big K, and as you guys already know, big K is basically the ratio of products over reactants raised to the appropriate coefficients. Okay, so what does K really mean? All right, well, if K is a really big number, okay, if K is greater than 1, then what we say is that means that the forward reaction is favored. Okay, and that makes sense because if the number is greater than 1, then that means the top is bigger than the bottom. So that means that the products are favored. Okay, so at equilibrium, you're going to have more products present than you are reactants. Okay, so therefore K is bigger than 1. Now, if K is really, really, really big, okay, then we can pretty much say that the only thing you have is products. So it would say that such a reaction goes to completion. So that would be reactions like maybe combustion, yes, okay, or maybe strong acids dissociating, okay, like hydrochloric acid and water, it dissociates 100%, okay, or, just a lot of your, CP Chem type reactions, like maybe double replacement reactions, any reactions that pretty much go to completion. Okay? Now, if K is less than 1, okay, well, that means that the bottom is actually bigger than the top. So therefore, we would say that the reverse or the backward reaction is favored. Okay? Or since the bottom is bigger than the top, then we would say that the reactants are favored. So in this equilibrium system, you'd have more reactants than you do products. So basically, this is pretty much like a lame reaction. It's just not going to appear to go very far. It's just, you're just going to be sitting there with mostly reactants. So if K is really, 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 really small, then the reaction basically doesn't occur because you pretty much have no products and lots of reactants. So let's say if we're looking at this reaction, the K for this is 10 to the minus 30th. That's outrageously small. You would have no measurable products. So we'd say the reaction just doesn't happen. All right, so for most of this unit, well, we're going to be in this area, but not super small, but pretty small K values. Okay, so equilibrium reactions. All right, so now this is a really important note, okay, is that if the size of K is really, really big, it does not mean that the rate is fast. Okay, so just because K is huge, that does not mean that the reaction happens fast. For instance, converting coal or graphite into diamond. Okay, is a very favorable process. It has a really large K value, but it takes centuries for that reaction to actually happen. Just keep in mind that the rate of the chemical reaction, okay, that has to do with the kinetics unit has to do with one factor only, and that is this guy right here, the size of the activation energy. So if the activation energy is really big, if the hill is really big, then the reaction rate's slow. Okay, and that has nothing to do with equilibrium. Okay, but we'll put all those pieces together. But just for now, if a large K value does not necessarily mean the reaction goes quickly. Okay, so kinetics and equilibrium, they are different things. All right, so now we're going to move on to something called Q. So we're going to predict the direction of a reaction. Okay, so basic idea is that if you have any reaction, you have concentrations of products and you have concentrations of reactants, you can calculate products over reactants, right? You can calculate an equilibrium expression. But if you're not at equilibrium, then you wouldn't say that's a K expression, you would call it Q. Okay, so Q is actually called the reaction quotient. Okay, and the basic idea is that Q is the exact same thing as solving for K. It's just if you're solving for Q, you're not at equilibrium conditions. Okay, so Q, a way to look at it is we say it's like a snapshot of particular conditions at just any random moment during a chemical reaction. Okay, the reason why we solve for Q is it can tell us what will this system do to reach equilibrium. Okay, so you can make predictions. So let's look at this example. So it says that the Kc, so the equilibrium constant for the following reaction is this number right here, okay, at 35 degrees. So in some random experiment, you have this many moles of NO, this many moles of Cl2, and this many moles of NaCl. Okay, and they're mixed in a 2-liter flask. In which direction will the system proceed to equilibrium? So in this situation, you have some of this, some of that, some of that. You have all three components. And you don't know. You don't know if it's going to go in the forward direction or the backward reaction or backward direction to reach equilibrium, okay, to reach kind of its happy place, okay? So what you do is you're going to solve for Q, and you do this exactly as if you were solving for K. So it's going to be the concentration of the products over the reactants raised to the appropriate coefficients. So you guys go ahead and plug those values in. Now be careful, these are mole values, and these brackets mean concentration, so you do have to make sure and convert them to concentration. So that might look a little something like this. Okay, so you guys go ahead and plug in your number, pause it if you need to, make sure you catch up to speed, and get yourself an answer. Okay, so I would pause, pause, pause. Okay, so hopefully you paused, and I'm just going to continue on. Your work would look something like this, and then you get this number of 2.8 times 10 to the 7th. So what's the significance of that number? Well, here's the thing. 2.8 times 10 to the 7th is bigger than the K value. 6.5 times 10 to the 4th. So we would say Q is greater than the K value. So what's that mean? So if Q is bigger than the K value, that means that you're top heavy, okay? You have too much product, okay, and not enough reactant. So which way are you going to shift to reach equilibrium or to get this number to equal this number? So in order to lower the number, you're going to have to shift the reaction to the left. Okay, you're going to have to get rid of some of the product, okay, and you're going to have to increase the reactants. So you're going to have to shift the reaction in the backward direction. So the way that we'd answer this question is that the system will proceed to the left to reach equilibrium. Okay, so it's going to rely on the backward reaction, okay, to reach equilibrium. So we're going to lessen the products, and then we're going to increase the reactants so that we can bring that number down to 6.5 times 10 to the 4th. Okay, so that's what Q is all about. So it's a tool, allow us to predict which direction a system will go to reach equilibrium. All right, to summarize, so we have this cute little box, okay? All right, so if Q is greater than K, that's exactly what we just saw. The ratio of products to reactants is too, hopefully you guys are guessing, too high. So therefore you have too much products, not enough reactant. So to fix that, you need to convert product back to reactants. So therefore, whoops, that's not reaction, reactants. Sorry about that. So the system is going to have to shift to the left to reach equilibrium, just like in the example. Okay, now if Q equals K, all right, well that's definitely the most ideal situation. The system is at equilibrium. Yay! So that means you're at equilibrium, so you don't have to shift. If Q is less than K, that means the ratio of products to reactants is too low. Okay, so that means you have too much reactant, not enough product. So therefore, you need to convert the reactants back to products. So basically, you have to shift in the forward direction. You have to do the forward reaction. So that would be shifting to the right to reach equilibrium. Okay? We're going to do a ton of Q problems. You know, the basic idea is that I'm going to give you a bunch of random conditions, okay, that are not at equilibrium. You solve Q just like you do K, but then you compare your value for Q to K to decide what to do from there. Okay? Alrighty, moving right along. We're going to do one more example, okay, and then we're going to practice all this stuff in class, okay, so don't worry. Here's another type of equilibrium problem that you could see. So the bottom line is if you know K, the equilibrium constant, you can calculate the equilibrium concentrations for that particular system. And now you are going to love these types of problems. It's very systematic. It's a lot like good old stoichiometry. Okay, so let's look at an example. So let's say the Kp value for the reaction is 55.5 for this reaction. Okay, if you start with this much H2, this much I2, and they're all placed in some kind of vessel and heated to 425 degrees, the system reaches equilibrium. What are the equilibrium partial pressures of the reactants and products? First thing you got to think about, what is this system going to do to reach equilibrium? Is it going to shift in the forward direction or the backward direction? Now this one is outrageously super easy. You only have hydrogen and iodine present. So what's the only option you have? What's the only way that this one could shift? it has to shift in the forward direction, okay? Because you have to make some products, okay? So it has to shift to the right, okay, towards products. You have to make some products. So that's easy. So you don't really have to calculate Q because this one's really obvious. Okay, now to organize our thoughts, we're going to construct what's called an ice table. Okay, now this is where you can kick in the, vanilla ice, ice, baby. Ding, 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 ding. Sorry if that's a little off cue. Okay, so ice table. I stands for initial. By the way, you guys are going to do at least 1 bazillion million ice tables before the end of second trimester. Okay, so I stands for initial. C stands for change. And E, of course, stands for equilibrium. Okay, so how does this work? First of all, we're going to write out the formula. So H2 plus I2 yields, hi, how are you, 2HI. Okay, now we're going to set up the chart. So I, initial, C, change, E, equilibrium. All right, so I means initial values. Now, this is Kp, so it's based on pressure. So you can just plug in pressure values, okay? So you don't have to worry about converting the concentration or anything. So 2.50 atm from the provided information, 2.50 atm. And then my HI was 0. So I already decided that this is going to proceed in the forward direction. So my H2 and my I2, well, they're going to go down so that you can make some HI, so that's going to go up. By how much will the H2 go down? It's going to go down minus X. How much will the I2 go down? Well, since they're in a 1-to-1 ratio, it's going to go down by the same amount. And then here's the real catch. How much is the HI going to go up by? Well, that's that stoichiometry piece. It's going to go up, so we're going to use plus, by 2x, okay? Because of this 2 in front. All right, so a little bit of stoichiometry that always comes out in this change row, okay? Now the equilibrium value is putting these two rows together. So the equilibrium pressure for H2 is going to be whatever my initial was, minus how much it went down by. It's going to be the same thing for the I2, okay? And then the HI, well, I started with nothing, so the equilibrium value is just going to be how much it went up by, which, as it turns out, is 2x. Okay? All right, well, you guys, these are my equilibrium values. So here's the thing. We can put that into the equilibrium expression. So that's where this piece comes from. So we're using Kp equals my products over my reactants raised to the appropriate coefficients. So my equilibrium pressure HI is equivalent to 2x raised to the second power. Okay, because that's how equilibrium expressions work. Okay, and then the H2 is 2.5 minus x. Okay, and then this one's 2.5 minus x. So I just put those together. Is that okay? So it's 2.5 minus x squared because these two are exactly the same. Okay? So this is my equilibrium expression. Now we already know what Kp equals. It equals 55.5. So could you solve this? Now I'm hoping that something jumps out at you. A really, 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 really easy way to solve this. You got squared here. You got squared here. So how can I get rid of those squares? Take the square root of both sides. That is a simplification that you want to catch every single time, okay? So squared on top, squared on bottom, you can take the square root of both sides to get rid of that squared. Okay, so what I want you to do is go ahead and go crazy with the math here, okay? Pause this and go ahead and solve this, okay? And make sure you get the right answer. So you're pausing, I'm just taking a break. Okay, so hopefully you got an answer. If you didn't, pause this and keep working on it. But just to make sure you do the crazy math, so we took the square root of both sides, okay, and then we had 2x over 2.5 minus x, and then the square root of 55.5 is 7.45. Then we multiply both sides by 2.5 minus x. Multiply both sides by 2.5 minus x. Did a bunch of foiling, simplifying, right? When it's all said and done, x equals 1.97. If you didn't get that, go back and figure out where your mistake was and make sure you can get that. All right, so you know what? We figured out x. Well, now, what was the question? Oh, yeah. Calculate the equilibrium pressures for all the players in this reaction. So now we're just going to take this and go ahead and actually solve for the equilibrium values. Okay, so that is going to look a little something like this. Okay, so the pressure of the hydrogen equaled the pressure of the iodine. They were both equal to 2.5 minus x according to my ICE table. So I plugged in 1.97 for x, and this is what I got for the hydrogen and for the iodine. And then for the HI, well, that was the equilibrium pressure was equal to 2 times x. So you just pop in your value for x and solve. All right, well, those are my equilibrium pressures. Okay, so I'm done. But if I were you, you want to make sure you did it right. You can check your answer by just plugging it in for K and make sure that you actually do get something close to 55.5. So 3.94, that was my HI squared over 0.53 twice for the H2 and for the I2, so I just squared it. And it does come out to 55.3. Pretty darn close to 55.5, so we'll say we did it right. So yay! Your first ICE table. Okay, now here's what you need to do. I need you guys to practice this. So for my class and Ms. Schneider's class, I want you to do number 52 on page 646. Pretty basic question. It uses an ICE table. Put it on a separate sheet of paper and bring it in and be ready to share. All right, guys, great. Thank you very much. I hope everything's making sense. And of course, we'll be practicing this a lot more in class. All right, thanks. Bye.